So I'm Thomas. I'm from CEA, so the French Energy Atomic Commission. And I will present you our work on Pulsar, which is an heterogeneous multicore based on RISC-V, and a little more about FD-SOI, Silicon Impulse Initiative. So, our work are funded by a European project called Things to Do, which objectives are mainly to build a large ecosystem around the FD-SOI in Europe, developing IPs, developing flows, and making demonstrators. And that is quite a huge project with more than 40 partners, including ST, Intel, and others, IGN, Synopsys, etc. Ah, thank you. So, what is FD-SOI? I don't know if you know this silicon technology. When you want to build some transistors, on the left, you have a bulk technology for CMOS with source, drain, and the gate. And in fact, it has many leakage within it. And so in FD-SOI technology, which means fully depleted silicon over oxide over insulator, the size of the channel is slightly reduced, and thus reducing the leakage, remove some bipolar transistors, parasites, which can cause latch-up, and also allows the body bias technology, which I illustrate here on the left corner. That means that under the transistor, you can put a tension that modifies the way the transistor behaves. On the right, I show you some of the effects, and yeah, we can show that this technology, which is in blue in this figure, is efficient at low frequency because of the low leakage, so it has low powers, is also able to work at higher frequency with higher voltage. And in this figure, we also represent that for a certain voltage, for example here, 0.9 volt, when you apply a body bias tension, you can move to this point and gain 10% of performance. So that means that with the same voltage for every transistor, by applying body bias, you can improve performance or decrease leakage. So now I will present Pulsar platform, which is our main work in the Things to Do project. Pulsar platform is a RISC-V big little-like heterogeneous multicore. So it has two small cores without FPU, with small caches, without accelerators, and two big ones. Here I present a boom core from Christopher Celio, and with a big L1 caches. It has also it will have a cooperating caching and instruction monitoring to manage power consumption, performance, etc. It has a complete interconnection generated by Synopsys Scala assembler tools with Axie4, HB, IPB network. It has multiple body bias zones in order to implement the fact that body bias can improve performance or reduce leakage. And also smart monitoring here with an CEA processor called Antix, which I will present later, and this smart monitoring will manage performance, aging, power consumption, and temperature through dedicated monitoring everywhere in the device. So, why construct an heterogeneous platform? Well, in fact, in SMP architecture, the accelerators, such as FPU, but also Neon accelerators, are used less than 5% of the time, but use a huge amount of space. For example, here on Cortex A9, I think, here is the Neon and the FPU size compared to the rest of the silicon. So that's why we are developing some functionally asymmetric multi-core processors, which have the same ISA, but without accelerators. And the main objective is to reduce silicon area of the chip, but maintaining the performance of critical section, for example. How we do that? For example, analyze the code and check where are the places where we need to have an FPU, for example. And then we schedule this part of the program on on the processor which has the extensions. Pulsar will be used in a demonstrator in Things to Do project for a pedestrian navigation system. Pedestrian navigation systems which will display augmented reality to the user. And so as it's presented here, it will be with stereoscopic cameras and IMU, so inertial movement unit. And this will improve the positioning from GPS by adding some feature from the images that can that the French National Geographic Institute can handle. Here is a more detailed Pulsar SoC with JTAG, interrupt controller, maybe the interrupt that was presented just before. The access buses, the antics, a lockstep mechanism between the two smalls and two big cores to be able to run fail-safe mode. DDR4, and also a serial link to the FPGA that will be in the demonstrators. So, as I said, monitoring will be handled by an Antix processor, which is a CEA tiny processor with only 70 instructions. It was designed for control. It's not a processor that under computation. It was really under made for control, and is able to change its functionality with some coprocessors that can be included or not in the pipeline. And some of the coprocessors are the body bias controller for the overall chips. It is fully SDK and is also silicon proven. However, the rest of Pulsar wasn't silicon proven, so we had to simulate it. The design was made in RTL and passed ISA and benchmark tests from the rocket ship generators GitHub depot. It's also able to boot Linux. The design space exploration was quite easy, especially moving from an FPU rocket to a boom processor was quite easy. However, we had some problem with increasing the number of core because LTL simulation is really slow. And we couldn't have used Spike, for example. I think everybody knows what Spike is. But it doesn't represent correctly the hardware, especially the small modifications or the caches. And we weren't able to add the heterogeneous part in it. That's why we move to emulation on Synopsys ZeBu emulators. So here is the standard way of performing simulation with rocket ship. So we have a compile test bench software, then a simulated part with VCS or model sim. And this part is the one that is really slow. So the first step was to remove the design, to move the design on the emulator by just adding a wrapper to the test bench. It improves the simulation time, of course, but it was not enough to have correct performance with a Linux boot, for example. That's why we moved on to transactional-based co-emulation, which simply remove the simulated LTL part by adding transactors. Transactors are software and hardware and are just way to pass message to the other part. These transactions are event-based, so are not performed every cycle, and that's why we really can increase performances by adding these transactors. The hardware transactors also is able to stop the design of the test clock in order to perform some routines and change the register value, for example. Here is an images of the flow. So we have our C++ test bench and our transactors that are compiled. In the hardware, we have our sources, then the hardware transactors. We synthesize them through standard synthesizers. Then we add some specific files from the emulator, and then we can execute the test bench. With this method, we achieve a clock under FPGA of 7 MHz. And so we were able to boot Linux in about 2 minutes. And with this method, it's still possible to create waveform and debug the hardware. And so for those who have used it, the Berkeley bootloader, we've made minor changes to it just to remove the spike dependency for the number of cores. And we also trap float error in order to handle the lack of FPU in small cores. We also change the Linux CPU info functions in order to really display the real ISA of each processor. And we were able to run the swaptions benchmark from Parsec with a really promising result. Especially, we correctly implement the trap, and we were able to choose on which processors the different thread should work. For other tests, we still have some issues, but that will be handled soon. Emulation is not the only way we can improve and we can accelerate software prototyping. We have a virtual prototyping platform named CESUM, which is based on System-C and is a fast multi-host and multi-ISA virtual prototyping platform based on QEMU. And so we have added the RISC-V QEMU ISA. It is fast, as I said, with 1,000 MIPS, and has also a large set of IPs integrating in it. In fact, it's a real framework to build a platform with different IPs, with different ISA, with different cores. System-C is not known to be real fast. That's why we have developed Scale, which is a parallel System-C kernel. And one of the really important things with Scale is that it is deterministic. That means that when you execute a program or a test bench and you have an error, if you rerun the same test bench, you will have exactly the same error at the same moment. And so it's as it say, it's increased up to 34 times on 64 cores. So here is our Pulsar virtual prototype. It is so with different threads for each cores. It has the antics for the monitoring and the whole memory hierarchy in it. And at the moment is able to run Linux. We also synthesize the Pulsar, the RISC-V part of Pulsar in order to check whether or not we can make it on real solution. And we have this figure, and we were able to run at 700 megahertz with the 4 cores and only consuming 0.6 watt. Having in a Things to Do project, we will be able to make a real chip with Pulsar. However, for those who doesn't have these opportunities, CEA Tech has made a silicon impulse, which helps in the industrials or startups or even academic to access to the FD-SOI silicium. And CEA will help the industrial or everyone to make some prototypes and then to production, especially for ultra-low power technology. Why? Because, in fact, FD-SOI was partially made by CEA Tech, and we had some IPs and a great experience with it. We can target many fields, for example, microserver because of the low energy consumption, consumer product because of the different voltage we can handle with this with only one chip. IoT because of the easy RF or analog integration, and also space and automotive because of its reliability. we can help an industrial in each of these steps for the feasibility analysis, for circuit design, maybe just for some prototypes with multi-project wafer, qualification, but we won't do the production. We can do that because of the in-house tools that we had. So, for example, this Veloce emulator, the wafer sort, the tester platform with more than 600 IOs, or the packaging tool. This platform is with many partners, especially ST and Global Foundries for the FD-SOI technology, Synopsys, and for the IP vendors, and other for the emulation and embedded solution. To conclude, I would say that with Pulsar, we have developed an heterogeneous platform based on RISC-V. We have developed fast way to test it, and we have encouraging results in it. The cyclical impulse helps other projects to make real chips, and our next step will be to implement the cooperative caches, the last steps, and continue our work on the virtual prototyping platform. Thank you for your attention, and if you have any questions.
Hi, Yansup Lee from Sci-Fi. It's pretty amazing what you did with the rocket chip generator and a lot of the other tools, including scale and things. So I guess I'm curious whether you're going to put the contributions back to the open source, and if you think you're going to do that, I guess I'm curious about your timeline as well.
Concerning feedbacks, the rocket chip generators is really powerful in its manner of generating LTL. With the different version, maybe it was sometimes quite hard to follow the different variation. One of the different, for example, for the parameter, the way you put parameters to generate the RTL change a lot from in quite 6 months, I think. And so it's maybe just a feedback is that it's quite hard to follow, but well, when we are really following the latest, it's really, well, it's quite easy to really implement it, and it's quite a pleasure to manipulate these tools. Concerning the heterogeneous part, as it's not tested in the rocket chip, it was sometimes hazardous, but it doesn't take too long to achieve the heterogeneous platform with it. And adding the other peripheral was really easy with the AXI interface for the Pulsar. I don't know if I answered the question, but
not quite. So
not quite.
I'm wearing a black uniform too, just no Sci-Fi logo on it. So I'll give it another shot. I think the question was pretty impressive work. Very cool. What are your plans with the IP? Are you planning to open that up and make it open source? And if so, when? Right? Was that?
Okay.
Good answer, by the way, but just wrong question.
One question. Okay. In fact, we don't know yet what we are going to do. Maybe we will part some of our work to the community, but we are not sure yet when.
We would love bug fixes to be pushed back upstream
Yeah, bug fixes. When we see bugs, in fact, we discuss on the mailing lists, and so we try to improve for the critical bugs. We already do that. Just for the development of IP or something like that, we don't know if we will share it.
Hi, I'm Olof from Camcom Research and Technology. I was wondering, you said you had issues with the speed using model sim of ECS, which is a quite common problem, but did you ever investigate using Verilator?
Use what?
A tool
I don't understand. Use what?
I mean, you have built a really impressive platform, but did you consider a tool called Verilator to speed up your simulations?
I've never heard of that before, so.
Design is in VHDL, I believe. Verilator is only for Verilog.
Yeah.
If I'm not wrong. It's a VHDL design.
It can handle also Verilog. There is no problem with that.
Hi, Vijay Subramaniam from Microsemi. You had about 10 milliwatts of leakage power in your implementation. Did you use power islands or state retention, or was the circuitry active all the time?
In fact, most of the leakage came from the memory activity, and I think in the model we used, it was 50% of activity. So it's always on, and
So it was always on?
always on. Yeah,
Okay.
we haven't implemented clock gating and etc.
All right. Thank you.